Okay, I will start. Any questions so far? Okay, today we will have a slightly shorter class. Okay, so I will talk about the spectral theorem for compact operators, compact normal operators. Of course, there is no spectral theorem for non-normal operators. It's only for normal operators. So I have to define what is normal. I'm sure all of you know what is a normal matrix. So definition. An operator. So it's appearing there. An operator T in B of H is normal if it commutes with this adjoint. If T star equal to T star T. Okay, so immediate consequence of normal operators. Yeah, you're asking something? Yeah. Okay, nothing. Yes. Okay. So remark, T is normal. Then 1. So this following thing is true. Tx equal to norm T star x for all x in H. H is always a Hilbert space. H is separable Hilbert space. Okay. It's not coming. So H is separable Hilbert space. Okay. Okay. The second one is a very easy consequence. T square equal to norm T square. In particular, further, this is a consequence of this 2 power n equal to norm T 2 power n. So proof, this is just a remark, but it's easy consequence. So norm Tx square, of course, you should consider Tx square, which is equal to norm Tx equal to.
Sir, the edge of your page is not visible.
Edge of my page is not
For
visible.
example,
So
yeah.
maybe I don't know why.
For every x in h, that h is not visible.
That
If
is not visible. Yes. Is it visible now?
yes,
Just
sir, it's clear.
yeah, it's okay.
Yes, sir.
Okay. Okay. So yeah, T star T x x. Okay, this is x. That's what I want. Okay. So but then since it commutes, T star T equal to T star x x, and that is equal to T star x which is equal to norm T star x square. So that's what we want. Okay. So norm Tx equal to norm Tx square. Second, T square, norm T square. By definition, this is equal to supremum of norm x equal to not less than or equal to 1, whatever. Norm T square norm T square. So T square, I just write it like this, T Tx. Okay. So, but this is equal to supremum of, yeah, supremum of norm x less than or equal to 1. But then we know that norm Tx is same as norm T star Tx for all x. In particular, you can, instead of x, you can substitute Tx. So this is same as T star Tx. But then this is equal to norm of T star. But this is equal to norm T square. which we have already seen. I mean, norm T star P equal to norm T square. This is called C star identity. We have proved in the last course, previous course. Okay? When we discussed adjoint, when we defined adjoint, immediately we proved this. So this is true. But then this just implies that, I mean, P power n is, the whole thing implies P 2 power n. We just have to, I mean, by induction. By induction, yes. Equal to norm T. Okay. So this is true only for normal operators. Okay. 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 So we want to prove spectral theorem for compact normal operators. And as I said, we can conclude this when we prove spectral theorem for general normal operators. From that, you can conclude this. We can get it as a special case. Since it is not very difficult, we will prove it now in this class. So it will give an idea what we are going to do. So before that, I hope all of you know the spectral theorem for finite dimensional. So if T is in MNC, finite dimensional, okay, or B of Cn, okay, T is normal, then there exists orthonormal basis E1 up to En, okay, contained in Cn, of course, such that T of and scalars lambda I in C, such that T of Ei, T of Ei equal to lambda I Ei. This lambda I may be repeating, it may not be different for all I. Okay, let's learn. Okay, so this you know, I hope, and this is equivalent to saying there exists a unitary matrix. I mean, this orthonormal basis need not be the standard orthonormal basis. This is some different orthonormal basis. So whenever you have two orthonormal bases, you can define a unitary map taking one orthonormal basis to another orthonormal basis. So this is same as saying there exists a unitary matrix U such that UT U star is, when you apply UT U star, that is like you are writing the same matrix with respect to another orthonormal basis. Okay, so is diagonal. I hope all of you know this. Okay, you must have seen it in linear algebra. So the generalization of this theorem, this is what is called spectral theorem. Spectral theorem, finite dimension. Okay. So it is this theorem we want to generalize to general normal operator. But to prove it for general normal operator, we need something called spectral measure and some integration with respect to spectral measure. But precisely this kind of theorem, whatever we have here, this will be true for a compact operator. Because compact operators are like some sort of generalization of finite rank operators. It's a limit of finite rank operators in the norm topology. The norm topology can be, any compact operator can be approximated by finite rank operator. So a similar spectral theorem is true for compact normal operator. So that's what we want to prove. Okay. So we want to prove this kind of this theorem for a general compact operators. Okay. So before that, let us define for a general B of H. This is not finite dimensional. H is any Hilbert space. Okay. And T in B of H is said to be diagonal operator, said to be a diagonal operator. I mean, a diagonal operator, usually we will say for, usually it is for a fixed orthonormal basis. When we say a diagonal matrix, it is diagonal with respect to standard orthonormal basis. But here we are saying any orthonormal basis. If there exists an orthonormal basis, En, any orthonormal basis, H, and lambda n, this is in L infinity. I mean, you will see that this has to be in L infinity because the operator is bounded. It has to be in L infinity, such that, or you don't need that. Just the lambda n. Maybe if it is bounded, it will be automatically in L infinity. Okay, so L infinity such that T E n equal to lambda n for all. Okay. I mean, we assume it's infinite dimensional. Okay, this is so. This is what is called a diagonal operator, or in other words, T of any x equal to any x can be written like this: x e n and a summation over n. But then this acting on that will be lambda n, lambda n equal to any tx equal to summation n equal to 1 to infinity lambda n x e n e n. You can see that this thing exists. I mean, for example, this is if you take the if you take the mod of this, then you can take the lambda n out because it's a L infinity. So you can take the supremum of that lambda n out, and the sequence is convergent in L2. Okay, so this makes sense. Okay, the sum makes sense. Okay, I mean this sum makes sense is equivalent to saying summation lambda n square mod lambda n square mod x e n square is finite, which is true. You can take the lambda n out, and because lambda n is L infinity, this is true. Okay? So if you have any L infinity, you can define such an operator, and if it is a diagonal operator which is bounded, it should be in L infinity. You can check. Okay, because I mean this T E n ENs are in unit ball, and this T E n this norm supremum should be bounded. Okay, that's because of that it's in L infinity. Okay, so this is what is called diagonal operator, and we want to prove the following theorem. Following theorem or proposition. T in B of H, a diagonal operator. Okay. Then T is compact. It's a compact operator. Notice that a diagonal operator is automatically normal. Okay, maybe. I mean, it's just clear. Is it clear? Should I prove it? Ten is lambda n en. So T star en is nothing but lambda n bar en. Okay. So it commutes. Okay. Maybe you'll come to that later. Okay. So a diagonal operator is compact. A diagonal operator is a diagonal operator with Ten equal to lambda n en. Okay. Then T is compact if and only if lambda n goes to 0. Okay. That's all. Okay. Proof. One way is just trivial. Notice that En converges to 0 weakly. This is just clear because since for x in H, x En goes to 0. This is what is called something like Riemann-Leibniz lemma. Okay? This thing is, I mean, the summation is fine. X En, this square is this summable. So Xen goes to 0 for all x in H. This means this is same as saying En converges to 0 weakly. In fact, this is an example I think I gave when we discussed weak topology. En converges to 0, but En has norm 1, so it cannot converge to 0 in norm. Okay, this is something which converges in weak topology, but does not converge in norm topology. Okay, so En converges to 0, and T is compact means T is weak norm continuous. Okay, so this implies Ten converges to 0 in norm. Okay, because T is weak norm continuous. Okay. So, but then TEN is lambda NEN. So this implies lambda NEN. And if you wish, you can take the norm, goes to 0. This implies lambda n. Mod lambda n goes to 0, so lambda n goes to 0. This implies lambda n goes to 0. Okay. So one way is clear. So we want to prove the other way. Prove this way. So suppose TEN, for some orthonormal basis En, TEN equal to lambda n En. And lambda n lambda n goes to 0. Okay, and lambda n goes to 0. Okay. So then we want to prove that T is compact. Okay, to prove T compact, it's enough to prove that T can be approximated by finite rank operators. So we have to get a finite rank operator which converges to T in norm. So notice that, T equal to T of x equal to summation n equal to 1 to infinity inner product x en, okay, for all x in h. Okay. Now define Tn of x equal to, maybe you can replace the earlier thing n by k if you wish. Okay. Then Tnx equal to k equal to, you just take up to n. Okay. X ek ek. Okay. For all x, define this. This is of course well defined. This is a well defined operator. Okay. It is just, it's also a diagonal. Sorry, there is a, you should tell me when I make mistakes. There is a lambda k here. There is a lambda k here. Okay. This is just this is just T of x equal to x. I have written nothing else. Okay. There is a lambda. So here I am just defining this Tn is also a diagonal operator with with the eigenvalues lambda 1 up to lambda n up to n, and after that it is 0. Okay, that is what Tnx is. Okay, then range of Tn equal to span of this. Of course, it is 0. These eigenvalues are 0 after starting from n. It's just span of E1 up to en. So Tn is finite rank. Okay, it is in B of h. Finite. So the claim is Tn converges to T in norm. That's what you want. It's a finite rank operator which converges to T. Okay. So how do we prove that? We want to prove Tn minus T. So we want to consider Tn minus T in norm, and we want to show that this goes to 0 as n goes to infinity. Okay. So how do we compute this norm? So for norm x less than or equal to 1, or x equal to 1 also you can take. Okay, you apply this x here, then you take the square, then that is equal to, this is Tnx is summation up to n, and Tx is summation up to infinity. So this you will get the summation. This is just summation over, you can put the norm here or you can take it inside because it's the orthogonal sum. So you can take the norm inside with the square. Lambda k, k equal to n plus 1 to infinity, lambda k, x en, x ek, ek, right? That's what we have. This is of course equal to summation mod lambda k square, k equal to n plus 1 to infinity, x ek, k square, right? Now choose, given epsilon greater than 0, choose n naught such that lambda k mod lambda k is less than epsilon for all k greater than or equal to 0. Okay. Then for all n greater than or equal to n0, this tnx minus tx square, which is this thing. Now this lambda k is less than epsilon, so you can take the epsilon square out. This is less than or equal to epsilon square times summation k equal to n plus 1. Here you do, I mean, you can take it from 1 to infinity also. Mod x ek square. Okay. But then this is less than or equal to epsilon square times norm x square. Right? This is, I mean, this is the summation from n equal to 1 to infinity is norm x square. So I'm just taking like this. So, but norm x square equal to less than or equal to 1. So this is less than or equal to epsilon. So this implies norm tn minus t is less than or equal to epsilon square for all n greater than or equal to tn converges to t in. Okay, so this we have to. So this implies t is compact. Fine. So we have proved if a diagonal operator, we have a diagonal operator. I mean, this is a diagonal operator means you have a orthonormal basis as eigenvectors and with some eigenvalues. Okay, and the eigenvalue should converge to 0. Okay, so that's what I hope all of you know what is eigenvector, eigenvalues, and all those things. I don't have to write it. Okay, okay. So the eigenvalue should there should exist. I mean, diagonal operator means there exists orthonormal basis as eigenvectors, and the eigenvalues are there. And if it is compact, it's compact if and only if the eigenvalues goes to 0. That's what we have. Okay. Okay. So fine. Now we want to consider. So I want to say that t is normal. So t is diagonalizable implies it's normal. T is diagonal. I said diagonalizable. I wrote diagonal. Is implies it's normal. So not the other way is normal. That is just clear because you want to compute what is t star. Okay. T star is just an exercise. T star en. We want to compute what is t star en. T star en. Okay. With any ek, okay, equal to en t ek, which is equal to en lambda k ek, which is equal to delta nk lambda k. Sorry, lambda k bar. I mean, because it's inner product, it will come out as lambda k bar. So this implies, so this is true for all k orthonormal basis. So you know what, I mean, then you know what is the inner product. This implies t star en equal to lambda k bar en. Okay, that's the only possibility. Okay. So now you know that t star t en equal to mod lambda k square, lambda n square en equal to t star. Right? So t is normal. Okay. So if it is diagonal, it's automatically normal. Okay. Now we prove another lemma. So I'm going fast because I don't see your reaction. Okay. Okay. So t is normal. Normal. So today I'm able to write it better. My handwriting is better. T is normal, and xy in H are two eigenvectors. Eigenvectors. That is tx equal to some lambda 1x and ty equal to lambda 2y. Okay. Then x is orthogonal to 1. If I mean eigenvectors with distinct eigenvalues with distinct eigenvalues with lambda 1. Then X is orthogonal. So eigenvectors of two eigenvectors whose eigenvalues are different, are different eigenvalues, are orthogonal. I think you must have seen this in linear algebra. It's the same proof. So how do you prove this? You just have to prove that the inner product is 0. You just have to prove that lambda 1 times this is equal to lambda 2 times this. Okay, this is equal to, you can take it inside, lambda 1 xy, but then this is equal to txy, right? Now you can take that side with t star y, right? But then we have seen, so I have to prove that. Okay, I will come to this. If we have looked at, we have seen it for diagonal operator. This is true for general normal operator. Yeah. So if x is an eigenvalue with if x is an eigenvector with eigenvalue lambda, then it's an eigenvector. It's eigenvector with lambda bar for t star. I will come to this. Okay, proof later. This is equal to, so this is lambda 2 bar. Now this is equal to lambda 2 x. Okay. So since lambda 1 is not equal to lambda 2, xy should be equal to 0. Okay. Okay. So why is that if it is normal? Here this is from star below. Okay. Now let us see what is star. Star is, if you take, so t is normal. Okay. T minus this lambda x. Lambda x star equal to t star minus lambda bar x is also normal. Okay. So this implies norm of t. No, there is no x here. I'm sorry. It should be identity here. Okay. So t minus lambda, or I just put lambda x equal to. This is, since this is normal, we have proved here. If it is normal, then norm tx equal to norm t star x. We proved it in the top. So this is equal to t star minus lambda bar x. Okay. So this implies if that is 0, this has to be 0. So this implies if t x equal to lambda x, then t star x is equal to lambda bar x. Okay. Okay. If x is an eigenvector with eigenvalue lambda for t, then x is an eigenvector with lambda bar, with eigenvalue lambda bar for t star. So that we have used here, and using that we have got that if x and y are eigenvectors with distinct eigenvalues, different eigenvalues, then x is orthogonal. So is it fine till now? One second, let me just.
Yeah.
Okay. I just. Okay, I could sit for a long time. Okay. So this, we have proved all these things. Okay. This will be used later. So what we want to prove is, so we have proved the result that T is a diagonal operator, then T is compact if and only if lambda n equal to 0, lambda n goes to 0. So the theorem we want to prove is T is a normal compact operator. Of course, if T is diagonal, it's automatically normal. So this thing hold only for spectral theorem can hold only for normal operators. So if T is a normal, compact normal operator, then there exists a set of eigenvectors or orthonormal basis, and eigenvalues lambda n, and lambda n goes to 0. That's what we want. So to prove that, we want to apply Zorn's lemma, okay, and do something. It's just Zorn's lemma. We have to produce one eigenvector and one eigenvalue. See, the infinite dimensional, it's not true that it's not clear that. I mean, there's something called spectrum. We will define. Something is a spectrum does not mean it's an eigenvalue. It's an eigenvector. Okay, so that need not be true. Okay, so I mean, if it is just something is not invertible, doesn't mean it has some kernel. Okay? That's not true. May not be on to. So we want to prove that there exists one eigenvector. Okay? And using that, we want to prove this. Anyway, we will do this again. Okay, later. The sound is coming. Okay. What do you want to prove? I want to produce one eigenvector with an eigenvalue. Okay, so that is the proposition. Okay. This is true for general normal operator. I think it's true for general normal. No, it's true for compact operator. Sorry, it's true for compact operator. In general, it's not true. So T is in B of H. In general, it is true for a spectrum, okay, but not for eigenvector. So here we are proving something about eigenvector. T is in B of H. T is normal, and it is normal compact. We have a normal compact operator. Then what? There exists a vector. There exists an eigenvector. X is in H, such that with eigenvalue well, it can be anything. Eigenvalue lambda with mod lambda equal to norm. That's all. It need not be exactly norm t, but modulus of lambda is norm t. Okay. So how do you prove it? First, I claim the following. On the unit ball, see, we have that this T is compact. So we have that T is weak norm continuous on the unit ball. Okay, that we have proved. So on the unit ball H1, define C by X going to consider this function. Let me not give a name for it. Consider X going to Txx. This is in C, of course. And this is in X, of course. Sorry, this is in H, of course. H1. We claim this function is claim. This function is continuous with respect to weak topology. Okay. Okay. So why is this true? So suppose we just have to check if some net converges weakly, this converges. Suppose x lambda converges to x, some net converges to this. then Tx lambda x lambda. This is equal to Tx lambda x lambda minus Tx x. We want to show that this goes to 0. Okay, this is less than or equal to Tx lambda minus Tx comma x lambda. Okay. Okay. Plus mod of, I have subtracted minus Tx, so that will be there. So this is Tx, and here I have x lambda, so x lambda minus x. Okay, this is fine. Okay, this is fine. I just use triangle inequality. Okay, now, and where x lambda, this is x lambda, this is contained in H1, this is in the unit ball. Okay, now Tx lambda minus Tx x lambda. This is less than or equal to norm Tx lambda minus Tx, because x lambda has norm less than or equal to 1. And this goes to 0 as T is, I mean, this T is weakly continuous. T is weak norm continuous on H1. Okay, so this goes to 0. On the other hand, Tx, this goes to 0 because x lambda converges to this, goes to 0 as, this is just the definition of weak convergence. Okay, so this goes to 0 because x lambda converges to x weakly. That's the definition. Okay, you can take any y here, it goes to 0. Okay, so we have proved that. So this the claim is proved. Hence the claim. It's fine. It's okay.
So in the first equality, it should be an inequality, right?
Here.
Yeah, in the
Sure.
Yeah.
Yeah, that's what I interpret. Correct. So this is triangle inequality, and we are using the weak norm continuity of T on the unit ball, and the fact that x lambda converges to x weakly. So it is just the definition, from that it follows. So this map x going to this is weak, it's continuous with respect to weak topology. Okay. So why do you want it? Now H1 is compact with respect to weak topology. Okay. And this function is weakly continuous. So supremum mod Txx x in H1. Oh, okay. I have to prove something. I'll come to that. So this is this supremum is attained in H1 because it's continuous. This function is continuous, and it is continuous with respect to weak topology, and the unit ball is weak compact. Banach-Arablo theorem says that it is weak star compact, but here weak and weak star topology coincides because it's a Hilbert space, and because of that, this supremum is attained. Okay. Okay. So there is something I have to prove. I will either prove it now or I will prove it later. Okay, because this is just we want to see how the spectral theorem. I think the proof is a little bit involved, so I'll prove it later. Okay, proof later. It's a fact. T is normal. Proof later. I'll prove it in the next class. Okay, T is normal. Then this is not true for general operators. Then norm T equal to supremum over norm x less than or equal to 1 mod Txx. We have to take Txy. We know that the supremum with Txy is norm T. But if we just take Txx, then also it's true for when it is normal. That's what this says. Okay. So this supremum, whatever we have said we have attained is norm T. Okay, so there exists a x naught in H1 such that, so if we are by the fact, okay, so this fact implies the following: there exists x naught such that norm t equal to this supremum txx equal to tx. Sorry, tx naught x naught. Okay. 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 But then this is less than or equal to norm tx naught times norm x naught. Okay, but then all this x naught is less than 1. So this is norm t times norm x naught. So this is less than norm t. So this thing implies that mod of tx naught x naught is equal to, because it's all equality, okay, this is equal to norm tx naught norm x naught, right? Then we have the converse of Cauchy-Schwarz inequality. We have proved in the last course, the previous course, that if the Cauchy-Schwarz inequality is an inequality, but the equality occurs if and only if those two vectors, I mean, we have proved that inner product xy is equal to norm x times, is less than or equal to norm x times norm y. It is equal if and only if x and y are linearly dependent. It's a scalar multiple of each other. So by Cauchy-Schwarz, the converse of Cauchy-Schwarz, Cauchy-Schwarz inequality, tx naught, there exists a lambda naught, there exists a lambda in C such that tx naught equal to lambda x. Okay, but then all these things have, I mean, it should have norm equal to x naught should have norm equal to 1, right?
Yeah, now it follows.
So all these things, this implies that norm t has to be equal to mod lambda and norm x naught equal to 1. All these things follow. Okay. Okay. That's all. So this is an eigenvalue. Norm t is an eigenvalue with x naught is an eigenvector with eigenvalue whose modulus is equal to norm t. Okay. Okay. So I have to prove this fact, which I will come to that later. I think this will follow from this, but I won't see immediately why that is true. It will follow from this.
Which one?
I have to prove a fact, no?
Oh, I see.
I mean, I proved the proposition up to a fact. I mean, modulo.
Yeah.
I have to prove that fact. So that fact will follow from this. So I don't immediately see that. Okay, so I will come to that later. All the other things are trivial. Okay, so now we are almost done. Okay, we have one eigenvalue. Now using Zahn's lemma, we will get we will prove that there exists all like that. So let me state the theorem. This is spectral theorem. Spectral theorem for compact normal operators. Okay, T in B of H is compact normal. Okay, then there exists orthonormal basis En contained in H and lambda n. This lambda n in C0, we have already seen that if it is compact normal, if it is compact and diagonal, then that has to go to 0. So this is in C0 such that Ten equal to lambda n En. Okay. For it to be a bounded operator, lambda n has to be in L infinity. But for it to be a compact operator, it has to be in C0. It has to lambda n goes to 0. C0 is the space of Banach space of all sequences converging to 0 with the norm is L infinity. Okay. Proof. So I hope all of you know. I mean, you consider all this Zahn's lemma, total order, and all those things, but I will directly write. I hope all of you are comfortable with Zahn's lemma, which we have already applied a few times. I think we applied few times, certainly more than once. Okay, so let me just write by Zahn's lemma. I don't want to write all those things. Zahn's lemma. There exists a maximal. You have to consider collection of all eigenvalues, eigenvectors. You have take a collection of orthonormal, mutually orthonormal eigenvectors. Okay? You take collection of mutually orthonormal eigenvectors for T. Okay, then it will have then by then with the partial order containment, one is contained in the other. Then there is a maximal element. It's then every chain has a upper bound. You can easily see by taking union and the usual thing. There is nothing different. So there exists a maximal element. Okay, there exists a maximal element, maximal set of mutually orthonormal eigenvectors. Set of orthonormal eigenvectors. Okay. Well, let me say k equal to 1 to n. Okay. Eigenvectors. Eigenvectors for T. So we have already proved that if it is diagonal, the lambda, the eigenvalue goes to 0. All those things we have already proved. All we have to prove is this is an orthonormal basis. That's what we have to do. Okay? This is an orthonormal vectors. We have to prove that it actually forms a basis. Okay. So let
The maximal set need not be finite, right?
maximal set need not be finite. Oh, sorry. Why did I write n? N equal to 1 to infinity. I want to write. This is just a mistake. Okay. I just want to write n equal to 1 to infinity. There is no. I'm not saying it's finite.
Yeah.
Sure. That's what I wanted to write. I don't know why I wrote that. Okay. N equal to 1 to infinity. That's what I want to write. Okay. Let K equal to span closure of this all this E. Okay. N. Okay. So we have to prove that this K is equal to H. That's what we want to prove. We want to prove that this En is an orthonormal basis. Then we are done. Okay. So we want to prove that K is actually equal to H. Okay. So suppose not. Suppose. I mean, we only need to prove. Let me write. Need to prove K is equal to H. That is, ENs are orthonormal basis. Okay. Suppose not. Choose. We have to prove that if there is a X in the orthogonal complement of K, it has to be 0. That's what we want to do. Suppose not. Let's say let P from H to K be the projection. Be the orthogonal projection. Projection. Okay. We have to prove it's actually identity. That's what we want to prove. Okay. Then we want to take 1 minus P, which is the projection onto the orthogonal complement of K. And we have to get an eigenvector there. And that will prove that if we get an eigenvector there, then that will prove that this is not a maximal. This collection is not maximal. That will contradict our assumption. So we are done. Okay, so that's what we want to prove. So to prove that, we want to consider 1 minus P T. So we want to prove that 1 minus Pt is the to prove that we want to prove that they commute. Okay, so first the claim is P and T commutes. If they commute, then it will become that P times T is orthonormal. is normal. Okay, if they commute, they are normal. I will come to that. Okay, P and T commutes. Why does it commute? Why does it commute? We have to prove TP equal to TPX equal to T of. So P is just a projection out to the span of the span of the space spanned by those orthonormal vectors. So that is just summation X EK. X can be, I mean, once you K equal to 1 to infinity, or you can put N. I mean, you have a X which you can write it as something in the space K and something in the orthogonal complement. And once you apply P, once you apply this projection P, it will kill something in the orthogonal complement. And you will only get the part which is in K, which can be written using this orthonormal basis. Okay, that's what it is. Okay? N equal to 20. I don't want to write the whole detail. It is just clear. I believe it's clear. Okay? So now this is equal to summation N equal to 1 to infinity. It's orthonormal basis for that, and TEN equal to lambda n. Okay? Because they are all eigenvectors, so TEN equal to lambda n. So this is equal to summation N equal to 1 to infinity X EN. This is just scalar lambda n EN. Okay. Okay. Now this is equal to summation N equal to 1 to infinity X. You can take the lambda n there as a bar. Okay. Now this is equal to summation N equal to 1 to infinity X T star EN, which is equal to summation N equal to 1 to infinity Tx En. Now you see this is just Tx expanded in terms of this orthogonal vectors. But then this is just the projection of Tx onto that, which is equal to P Tx. Okay. Is clear? Tp equal to Pt. Is clear?
Yes.
I just expanded it in this orthogonal. In the, I mean, there is something I have missed it. I mean, but it is clear. You have to write the x as something in K and something in the K per. And once you apply P, the something the K per part will be killed. And that's what I'm using here also. Okay. This is just PTX. The K per part will be killed. Okay. So TP equal to PX. So this implies TP is normal. That is just clear. TP. So TP star TP equal to P T star P equal to P T star P, which is equal to, you can write it whichever the way you want. TP. I mean, you can, since P and K commutes, you can write it as TP, and you can take the P is self-adjoint. So if it P commutes with T means it commutes with the star also. You just take star. In this equation, if you take star, it will commute with star also. So you just need TP star. Okay, it will commute with star also. So it is clear. Okay. So this is normal. So this is normal. This implies 1 minus PT is also normal. Normal. Okay. And T is compact. Anything I mean, if you, okay, I didn't say that. If you multiply a compact operator, then that's also compact. That is just clear. Because any compact operator can be, any compact operator can be approximated by finite rank operators. So if T can be approximated by Tn, 1 minus Pt can be approximated by 1 minus Ptn. Okay, because multiplication is jointly continuous with respect to norm. Okay, so this is also normal and it's compact. I mean, we proved that finite rank operators are two-sided ideal star closed two-sided ideal. But it's also true. It's also true for compact operator. Same thing will work because we are just taking the closure. Okay. So we are just taking the closure in norm topology, and multiplication is jointly continuous. In fact, it's jointly continuous. Okay, it's not just one way. It's jointly continuous. So because of that, that is also an ideal. Compact operator is an ideal. Okay? 1 minus p is also normal compact. So this implies there exists a vector x in 1 minus p h in this orthogonal complement with norm x equal to 1 and 1 minus p t x equal to lambda times x. Okay, and mod lambda equal to norm of 1 minus p, like whatever. But then this is same as, I mean, 1 minus p commutes with t, you can take it, so this implies tx equal to lambda x. That's also true, right? 1 minus p commutes with t, so you can take 1 minus p there and it will tx equal to lambda x. So this implies this en is not maximum. It's not maximum. Contradiction. Okay. So this implies p equal to, it has to be p equal to 1, k equal to h. So we have proved the spectral theorem for compact operators, except for the fact I mentioned, the supremum of txh, which I will prove in the next class, or we will see later. Okay, when we discuss something more on that. That's true for general normal operator. Okay? So we have done this. So any doubt anywhere?
Why is Tx equals lambda x?
Say it again.
Like Tx equals lambda x.
How is tx equal to lambda x? 1 minus p commutes with this, and x is in the range of 1 minus p. So
Okay.
yeah, so tx equal to lambda x.
Okay.
Since h, okay, because of fine.
Yes, sir.
Okay, so if so, I will stop here today. We will meet next week. Okay, so next week, from next week, we will start. So these are all general thing. I mean, these are all very easy thing. So we will. You can look at this, whatever I said about normal operator and this compact operator also. You can look at the book by Sundar, where the title of the book is Operators and Hilbert Spaces. Okay.
So there are two books, right? So
That's what I'm saying. One is Spectral Theory. We are actually going to do Spectral Theory, but we are not going to refer the book on Spectral Theory, because that involves, see, usually the proof of spectral theorem involves what is called a Hahn-Hellinger theorem, which is a very deep theory in measure theory. It will take several classes, you need to sit for several sessions to prove one just theorem, which is a deep theorem in measure theory. So it will take a long time. I mean, it's not measure theory, it's a representation of C of x. Okay, representation theory of the algebra C of x. So we can avoid that. There is a proof by Halmos. So, but then in Sundar's book, it's written in a simple language. Okay, where it's not difficult. So we will follow this for this course, for this purpose, operators on Hilbert space. So we will look at this book. Okay, not the spectral theorem book. Maybe if we have time, we will do something from the spectral theory book later. Okay. So this is what I will refer, and I will faithfully follow this with some deviation if needed. Okay, that's all. If I can simplify something, I will slightly deviate. Okay. Okay. Any other question? If not, I will end the session. Okay. Goodbye.
Thank you, sir.